So this is a 2021 paper module one. So let's have a look at this, right? So number 1A says that americium 241 is a radioactive isotope used in the domestic smoke detectors. Americium 241 has a half-life of 432 years and decays by emitting alpha particles to produce neptunium. Define the term radioactive isotope. Just raise your hand and go ahead.
So a radioactive isotope is an isotope that is unstable and undergoes nuclear reactions to become stable.
Unstable isotope, lovely, that undergoes. So it's that decays spontaneously or undergoes nuclear reactions. So you could have nuclear reactions, right, or undergoes spontaneous decay, right? To emit what? Did you speak about emittance or something?
No, I didn't.
Or just generally nuclear reactions to repeat what you said?
Um, Undergoes nuclear reactions to become stable.
Okay.
But you can say while emitting different or while emitting particles or something
Particles.
like that.
Okay. So okay, you could say while. Yeah, while emitting. Or yeah, while emitting particles to become stable. Hopefully nobody has an issue with that definition there. So give two names and symbols, right? For other radioactive emissions, right? So the names and symbols for two other forms. So we have alpha decay, right? So what are the other two forms that we look at?
Beta and
Beta
gamma.
and gamma.
All right, so we have beta. So hold on. My B's and my D's get mixed up all the time. All right, so beta, right, and then we have gamma, right. Three uses of radioactive isotopes.
during medicine or in
X-rays.
Okay, hold on. I don't want everybody to be speaking at one time, so I don't get very confused. Okay, so
X-rays.
sure X-rays and then gamma ray.
medicine.
Okay.
Oh, sorry, medicine is too vague. What? As tracers.
Okay. So carbon dating. Somebody mentioned something that is not normally said all the time. Where?
So what about energy generation?
Yeah, energy generation is there. Um, somebody said something about, is it the sterilization? Um, this somebody named Kev. You have your hand up. You can go.
Oh, sorry, that was a mistake.
All right, no problem.
Sir, the
I'm listening.
tracers is different from the medical thing.
Oh yeah,
The
sorry.
medical would be the radiotherapy, and the tracers would be detecting smoke, detecting something like that.
No, when I
Considered
said
smoke.
tracers, I mean when you consume the isotope and them follow it through your body.
So like
Yeah, that'd be like the smoke detecting.
Yeah, I think they're both tracers in medicine and industrial uses and stuff.
yeah. So they are both. Right, you can have medical traces real. You can have smoke detection. There are many other things. Somebody said in a pill form. Somebody said something about what is it? What is it? The sterilization of instruments.
Yes, sir. Somebody did say it in the messages.
So
It's
if
used to sterilize medical equipment.
okay, sterilization is one. Medical.
It isn't explosives.
Yeah, I mean, okay, using explosives. Using explosives.
Oh,
And pacemakers.
Pacemakers. All right, so
Energy.
yeah, energy production, energy generation is there for your. So we have that. So general X-rays are using to produce X-rays. I don't remember which one does that. We have tracers like iodine 231. We have americium 24. What is it? The americium was even mentioned up here. Why did I forget the name? 241. Um, Sterilization. Though I don't actually have the example for the sterilization one. Using explosives, we have uranium generally, or um. Why did this duplicate? All right, so we have uranium, or we could use plutonium specifically. We can have pacemakers as well, general pacemakers, radiotherapy. So all of these things, general radium for the radiotherapy, etc. And why did it disappear? Okay, I'm not sure if you guys saw where all that I wrote a while ago just disappeared. Let's just put carbon dating here. Um,
sir.
energy.
Sorry, sir.
Go ahead.
Sir, excuse me.
Go ahead.
For this question, would it have to list which, like, give an example and then give
Yeah.
give an
So
example and say what it, like, explain what you say, what you list, like just a brief explanation, like one sentence.
yeah, something like that. I would prefer if you do that. So a brief sentence of what it does. The 2, 3, 4 Mexican. So we would just basically you can't just put tracers or stuff like that. You would engineer it. So you can use the chain reactions, right? From actually what would you say no? From propelling a neutron into a uranium atom, right? So you can use that to produce chain reactions to generate energy, right? 212 is it 212? Iodine 212 can be used as tracers for to research thyroid activity. Carbon dating can be used to date objects, right? Organic
It's
materials.
131.
131. All right, thank you. 131. All right. So we just need to like write a general line. So we use this for that, right? Basically. So we use this isotope for that. And then you should be able to get the 3 marks from that. Alright. Determine the value of A and Z in the following equation.
It's also 235. Uranium 235.
235. Is it not 235 up there? Oh my. Alright, so 235.
So 2, 3, 4.
Alright, my bad. My bad. Thank you so much. Alright, so let's do this here. With the americium here, what's happening? If we have helium, if we have the this type of decay, right? What's gonna happen to the mass number?
Decreased by 4.
So we're gonna
Decrease
have
by.
lovely. So 241 minus 4 is going to give us 237. So A, right, is A should be 2. Let me just write it big then. A it should be the 241 minus 4, which is equal to our 237, right? And then here our 95 needs to be decreased by what? For Z,
By 2.
2.
95 minus 2 is
93.
all right. Moving on with our lives. The element rhenium consists of two isotopes, rhenium 185 and rhenium 187, right? In the atomic ratio 2 to 3. Calculate the relative atomic mass of rhenium to 3 significant figures. Just raise hand and go ahead. Go ahead.
Alright, so the formula is relative atomic mass equal mass of isotope times abundance.
Okay, so the relative atomic mass, the RAM, is equal to. Hold on, let me fix that. If I could type that would. Okay, let me type it. Let me type it. So we're saying is the relative atomic mass.
Yeah.
Mass is going to be equal to the sum of what?
It's the mass of the atom. The isotope actually.
So that's what we call the isotopic
The
mass.
isotopic mass times the
Times the abundance.
ratio or mass.
Abundance,
Yeah.
right? And then we're going to actually divide by 100. That is that. So the sum here is just to represent the sigma that would go there. All right, so we have that there. So what's happening here? What should we do?
So you have a 2 to 3 ratio. So instead of dividing by 100, you're going to divide by 2 plus 3, which is 5. So you're going to have 185. Can't really see good. 185 times 2, because 2 is what it corresponds with, plus 187 times 3 divided by 5.
Yeah.
All right, so that's what we should do. What are the values that we're getting? So this 2 applies to this one over here, and the 3 applies to this one over here, and then together this equals to 5. So we use the 5 to do that. What are the values that we're getting now?
186.2.
186.2.
Lovely. So it's equal
Sir?
to 186.
Sir,
Go ahead.
hold on, let me do
It's
something.
just, it's just the,
Repeat.
it's just to three significant figures. So yeah, never mind.
Oh, 180. Wait, is that the significant figures then?
Yeah.
Yes, sir.
Okay. So the 3 significant figures, we'll just see. Right. C no. A student was asked to investigate the relative accessing ability. What is this? This is not unit 1. This is not module 1, I mean. What is this? Alright, so a student was asked to investigate the relative oxidizing ability
Sir, that's what you
of a group element of the halide, right, chlorine. List 2 chemicals and 1 piece of apparatus the student may carry out for this investigation. Somebody raise their hand, go ahead.
Sir, chlorine.
2 chemicals, chlorine, chemical.
Chlorine and potassium iodide.
Chlorine.
Chlorine has this gas.
Yes, sir.
Okay. So
Sir, what was the last mass for the previous question?
186. So chlorine gas and what other chemical is it? Potassium iodide you want to use? Okay, first of all, what are we doing here? What is it? What's the process that we're gonna use? and then we outline the chemicals and apparatus. What's the process you guys using?
We can use iron and the halide.
Iron?
Yeah.
Why?
Well, we could have used potassium bromide.
Also, you just want another halide
Because
other than chlorine.
all halides except iodine is going to oxidize iron from 2 to 3.
Oh my, interesting. So Fe, which one you want is bromide? So FeBr3,
Yeah.
and what's the apparatus you're going to be using?
It could have been test tube or probably a beaker.
Oh boy. All right. Interesting. You know what I would do? I don't know. I would probably like use a standard hydrogen electrode and also to something, and then use reducing power to now convert it to oxidizing power. All right, but let's look at this now. Describe one physical change that the student may observe while carrying
Sir,
out.
do you have to use iron?
Will we have to use iron? I think they're using iron so they can see a color change in the ions, right? So they're using, it could be silver bromide. Technically, if it's silver bromide, we should be seeing bromine gas being evolved. So yeah, it does. I don't think it's a have to for the iron here. I don't think it's a have to. All right.
Sir, could you use potassium iodide?
Okay, would chlorine displace iodine? Iodine?
Yes.
Yeah.
Yes, sir.
Alright,
Sir,
so
could
it could
you
work.
could you use potassium bromide?
Yeah, okay.
Yeah.
So by the way, the metal itself doesn't have such a huge impact. By the way, it's just a halide, made a different halide that chlorine can actually displace. Right? So the metal is, it's not that if you change the metal, it's wrong. We just need two chemicals that will be suitable. Alright. Say one physical change that we'll see. Well, physical change that the student may observe.
Could you refer to the color change from green to reddish brown
The solution.
of the 3 plus?
Why would it be from green to reddish brown?
Well, the solution would be reddish brown, but green would have been F2. So that's why I said that.
So my issue is how would this become?
Sir,
Okay, it
sir,
can become F2 if it's FeCl2. Go ahead.
yeah, I was saying that it's investigating the oxidizing ability, so I want to know which one would oxidize iron 2 to iron 3. So the observation that you would make would be the color change from the green iron 2 iron to iron 3. The red brown or yellow brown or whatever.
Yeah, but the thing is, right? What the iron that we're using is 3 plus. So if we're going backwards, is that still oxidation?
No, sir, why are you using 3 plus?
We need the
It
iron
should
2
be
plus. So which compound has iron in 2 plus?
I don't know. You could probably just write the ion Fe2 plus. That's what I would do.
Oh, you were just, oh, I get what you're saying. You just cheat the system and just write Fe2 plus, and that is the answer, and we'll move on with our life. You could use iron oxide or iron sulfate.
You could also use a hydrogen sulfide. It's going to oxidize it to sulfur.
Yeah, well, sulfur dioxide, LVSO4. We could use that because that is going to be in the 2 plus state. So when you actually do the solution now will actually change from your Fe2 plus, well, your green, no, not red brown. Yeah, it's red brown. Because if you're gonna be looking at the iron there are other ways to look at it, but that is fine. Looking at the oxidation of the iron. Alright? Identify the oxidizing agent that the student may use while conducting the reaction. So what's happening here? You say to identify the oxidizing agent. So what is the oxidizing agent?
The halogen.
The halogen. Alright. So we I'm prepared to write just the halogen. So in this case,
Chlorine.
Chlorine gas.
Alright, the halogen or the halogen. Write the relevant half equations to illustrate the chemical changes that occurs within each element used to carry out reaction.
The chlorine gas will be reduced to Cl minus, and the iron will be oxidized. The iron 2 will be oxidized to iron 3 plus.
Okay, since I like to write oxidation reactions first, Fa2 plus. So with that Fe2 plus, right, is going to be added. It's going to gain an electron, right? Oh, it's going to lose an electron. My bad, right? So we're going to have a. How do I exemplify an arrow? That, I guess. And then we're going to get this Fe3 plus. And then we're gonna look at the chlorine. Wait, so what happens to chlorine?
Oxidized.
Alright.
It's reduced to Cl minus.
So we're gonna have electron and negative electron, and then what we're gonna do is get this and Cl minus. And then you're writing your state symbols.
Third Cl2 plus 2 electrons.
Oh. 2, 2, 2. Alright. Each of the following terms define the molar mass. What is the molar mass of a substance?
This refers to the total number of protons and neutrons within an element.
That's the atomic mass of the substance, not the molar mass.
It's the mass of 1 mole represented in gram per mole.
The mass of 1 mole represented in grams per mole. Okay, lovely. Go ahead. Somebody was saying something. Okay, no? So that is the only answer. Okay, let me look at the chat because people typing, Alright, so Aaron says the molar mass is the mass of the compound per mole. And then Chet says the 1 mole of a substance measured in grams. And Matthew said the mass of 1 mole of substance measured in grams. Okay, so that's basically the same thing. That's what I say. So the mass of 1 mole of a substance measured in grams. What is a mole though?
A mole is the amount of a substance that contains the same amount of particles as there are carbon atoms in 12 grams of the carbon 12 isotope, I believe.
Okay. The amount of substance that contains the same amount of atoms in 12 grams of the carbon, well, it would be carbon 12 isotope, right? And then that would be 6 times 10 to the power of what? Avogadro's constant?
23.
23 well,
Particles instead of atoms.
yeah, particles are molecules or something like that. But particles is better. It's more clean. Alright. Okay, let's go. Ammonium sulfate reacts with aqueous sodium hydroxide as shown in the equation below. A sample of ammonium sulfate was heated with 100 centimeter cubes of 0.5 mole per dm cube aqueous sodium hydroxide. To ensure that all the ammonium sulfate reacted, an excess of sodium hydroxide was used. Heating was continued until all the ammonia has been driven off as a gas. The unreacted sodium hydroxide remaining in the solution required 27.3 centimeter cubes of 0.6 moles of hydrochloric acid for neutralization. Alright, calculate now the original number of moles of sodium hydroxide in 100 centimeter cubes of this 0.5 mole per dm cube of aqueous sodium hydroxide. What is the first thing that we'll do here? The first thing indeed should be reading the question.
1 dm cube.
Mole is equal to
You can say 1
sometimes.
1 dm cube
Go ahead.
of ammonium sulfate
Okay, what are you trying to do?
contains 0. I'm working.
Oh, okay. No, like what is
Okay.
the step? I want. What are you planning to do? What's the word?
That's how I do it. That's
Yeah,
how I know whether or not I'm multiply or divide.
No, I get what you're saying. Oh, wait, multiply. Okay. What I'm asking is, what's the first thing that you should be doing? Because you're doing something. What is it?
Oh, you're
Mm-hmm.
you're calculating the amount of moles in 100 cm cube of ammonium sulfate.
Okay, so that's the step thing I wanted to get. But your method is fine, right? So let's look at this. Step 1 is just calculating the number of moles in the 100 cm cube, right, of the ammonium sulfate. That's what you're doing first. Everybody agrees with calculating that in the ammonium sulfate first.
Question: Isn't the 100 cm cube in the sodium hydroxide and not the ammonium sulfate?
Well, let me read. Yeah, wait, hold on. Sodium hydroxide, yeah. So of the NaOH. Right? So what's the next step? With that information, what is it that you do?
Convert it. That's what the question is asking. No, you're going to use mole ratio to find out how much reacts. Sorry. So you find out how much mole is in that, and then you're going to use mole ratio to figure out how much actually reacted in the reaction.
Sir, I think it's only 2 marks. Well, it's only 2 marks. I think all you have to do is convert from the dm cube to the 100 centimeters, because that's literally how many moles there are in the 100 cm cube.
And plus it says the original number of moles, not the amount of moles that was used. So just use regular moles equal concentration times value. So the 100 centimeter cube and the 0.5 feet concentration.
Alright, so to convert CM cube to DM cube. Alright, lovely. So we're seeing that there, right? So what is it that we do? No. Okay, so let's look at that. So we're saying no, that we're just looking at the number of moles in here, right? Okay. So converting 100 sim cube to dm cube is what? What do we do? We divide by 1,000, right?
Yes, sir.
All right. So it's just the 100 divided by 1,000 to give us this will be 0.1, right? dm cube. All right. So what is it we do now? If we're trying to find the number of moles, the number of moles is equal to what?
Concentration times volume.
Concentration, right, times the volume, right? And if we have a concentration and if we have a volume, right, we should be able to get that. So what is the number of moles? What concentration we're using and what volume we're using? Let me check the chat. Just in case it's in the chat and people speak. Expecting me to just read it. What's happening now? So what's the concentration we
Use the 0.5 as concentration.
So they use the 0.5 and then we're timesing that by
0.1, sir.
0.1.
All right, so we have that 0.5 times 0.1 is going to be what? 0.05.
Yes, sir.
All right, and what is that? Well, 0.05 moles. Okay, so that is that. Calculate the number of moles of hydrochloric acid in that amount. Would it just be the same procedure, right? Moles times the volume times the concentration, right? Yes, no, maybe, kind of, ish.
Yes, sir.
Okay, so it's the same thing, right? So it's at the 27.3 and we divide it by 1,000. And what's gonna be our answer there? That's gonna be 0.0273, right? And then we'll take that now, and we now take this times it by 0.6. And what's our answer here?
Zero point 0.01628.
Okay, everybody's fine with that? Everybody's fine with that? Okay. All right, so that would be to how many?
Wait, the same formula as above?
Yes.
Okay.
So what's this? What's the?
Can you please scroll back up?
Give me one moment. 1 6. I'll just leave it at that. All right. Scrolling back up. We can continue now.
Okay, thank you.
Lovely.
Yes.
All right. Barcode area sequential. Sequential barcode. All right. Deduce the number of moles of the unreacted sodium hydroxide by the hydrochloric acid. So the number of moles of the unreacted sodium hydroxide. What would that be? How would we do that from what we have here?
Sir,
Go ahead.
the same number of moles.
The same number of
The
moles.
same number of moles in the hydrochloric acid, in the excess hydrochloric acid.
that you just calculated, it will be the same number of moles for the second question after.
Okay, so why? How do we get that reasoning? How? So the unreacted sodium hydroxide remaining in the solution required this amount of this, right, to react. Okay, so why would it be the same amount? I want somebody to explain to me why it's the same amount. Go ahead. Is it because it's a 1-to-1 ratio?
Yes, sir. I think when you react the unreacted sodium hydroxide with the excess hydrochloric acid, you'd see it's in 1-to-1.
Okay, so it will be the same amount. So the number of moles of hydrochloric acid is equal to the number of moles of sodium hydroxide, which is 0.016 moles. I don't want us to just do things because doing things for the sake, right? Because we need to do them and understand why we do them so we can apply them in any situation. Calculate the number of moles of sodium hydroxide which reacted with ammonium sulfate now. So how much reacted with ammonium sulfate? So if we have this much reaction with this sodium hydroxide, well, let's look at this. How much reacted with that ammonium sulfate?
Is the 0 point, sorry,
Go ahead.
is the, for the 1 mark question, is the 0.016 the amount of sodium hydroxide reacted or unreacted? Could somebody explain that to me, please?
It would technically be the one that unreacted. Okay, so what's they're saying? Let me see if I can get that. Right? So ammonium sulfate is reacting with sodium hydroxide, right? So this reaction is happening. What's happening is here is that to ensure that all the ammonium sulfate reacted, right, and excess of sodium hydroxide was used, right? The unreacted sodium hydroxide remaining in the solution required this amount of hydrochloric acid to neutralize, right? So if we look at the reaction now, we have excess sodium hydroxide existing, NaOH, and what we're doing now is adding hydrochloric acid to it now to neutralize it to sodium chloride plus H2O. Sodium chloride and H2O. Right? And what we're saying is that the same amount of moles of acid it requires will be the same amount of sodium hydroxide that was there. Because a 1-to-1 ratio. That make more sense?
Yes, sir. Thank you.
Alright, no problem. And now what we're looking at here now is calculating the number of moles of sodium hydroxide which react with ammonium sulfate. So that's where we are. Let's go. Who has this on the... Who has this done? What would we do now? So we need to know how much of sodium hydroxide react with ammonium sulfate. So what's happening here? What would we do?
Oh wait, sir, hold on. Where did we get the 0.016 from?
Okay, the 0.016, right? We got it from here, right? This reaction. So what we did was find the number of moles of hydrochloric acid, right? The 0.016, right? And then because it's in 1-to-1 ratio with sodium hydroxide, the unreacted sodium hydroxide, then it would be equal to the number of moles of sodium hydroxide there. All right.
Okay, sir. I realized that I had a different value for the other one. That's why I didn't realize it was 0.016.
Okay, no problem. And now what we're doing is looking at this. What are we going to be doing? We know how much unreacted sodium hydroxide was there. So what do? Do we just minus the unreacted from what has reacted?
Yes, sir.
Okay, so we're minusing the unreacted from this.
it would have been
Like
the
original.
unreacted from original because we're trying to find the reacted.
Okay, wait, question. I didn't hear properly what you said a while ago. So are you reaffirming that you minus your unreacted from the original?
Yeah, that's what I did.
All right. Anybody has any issues with that? No issues.
Sir, wouldn't that be to find how much of it did react? But you're trying to find how much of it is unreacted.
Oh, what we're trying to
So I don't
find.
think you would subtract.
Hold on. What we're trying to find is how much did react with ammonium sulfate. That is what we're looking for. Right? So how much did react with ammonium sulfate? Right? So what we did, we add this amount, the original amount, right? And to ensure that all the ammonium sulfate was reacted, we added sodium hydroxide now in excess, right? So now what we're doing is removing the excess in order to get what we actually had in the amount of sodium hydroxide reacting. Does that make sense?
Yes, sir.
So in that case, that is the reaction.
So it's a 1-to-1. Oh,
Okay, you're asking if it's a one-to-one ratio. It is not a one-to-one ratio. All right. So if that is the number of moles of sodium hydroxide that reacted, right, with the ammonium sulfate, we must now know that this is a 2-to-1 ratio. 2-to-1. Therefore, we must half the number of moles in order to find the number of moles of this. Agreed? All right. So let's look at that now. We take the number of moles now of sodium hydroxide. Oh, please stop. Please stop. Okay. So 0.034. And what will we get? 0. If I can read this properly, 0.017, right? Moles. So it's
yes, sir.
0.017 moles. Right? And now the mass now. How do we find the mass from the number of moles? This is equal to
Moles times molar mass
Yeah.
times the molar mass.
most times the molar mass, right? What is the molar mass of sodium? Well, I was about to say sodium ammoniate. Sorry about that. Um, what is the mass of ammonium sulfate? The molar mass of ammonium sulfate. If you look at ammonium sulfate, what is the mass?
132 gram.
132. Okay, what's the mass of sulfur?
Yes, sir.
What's the mass of sulfur? Is it 32? Mass of sulfur.
Yes, sir.
Mass of, if the mass of sulfur, you sure the mass of sulfur is 32? Is it flat? We just use relative atomic masses in this case. Wait, in Unit 1 chemistry, it's 32.065, but just put 32. Okay, 32, right?
Sir, it's just 32.
Okay, 32 plus oxygen is going to be what? 16 times 4, right? And then if we add 8 hydrogens, just adding 8, and add 14 times 2. Answer is 132. Lovely. Alright, so as you stated above, as you stated correctly before, the person said 132, 132. Right, so what we're going to be doing now is just taking that 132 that we get for the mass of our ammonium sulfate. Right, so the 132, I'm timesing it by 0.017, and that should give us 2.244, and this is in watts. What's the unit? What's the unit?
Sir, grams.
Grams, lovely. All right, so
Sir,
now,
can I see the question above, please?
above, for which part of the question? This part?
Can I? No, IV. Can I say IV?
Okay, for
Thank you.
all right. So now we must write the ionic equation, including physical states for the reaction between ammonium sulfate and sodium hydroxide. So we now need to derive our ionic equation between ammonium sulfate and sodium hydroxide.
It's not 2.2, you know. It's 22.
It's 22?
Yeah.
Hold on. It's not 2.2, it's 22. Okay, let's go.
I got 2.2.
Hey, what's happening with the... Oh, where did 22 come from? 0.017 times 132 should give us 2.2.
Wait.
Did you misplay something?
It's 0.03362. That's what I got. I didn't and divide that by 2 because I got that as the number of moles of sodium hydroxide.
Alright, so now I'm confused. Alright, hold on. What did you do to find the number of moles of sodium hydroxide?
Okay, it's me. I left off the 0 instead of the in front of the 0.168. Sorry.
Okay, no problem. Never say sorry. Alright, in this case, in this context. Alright, so write the ionic equation. Is our ionic equation gonna look like? The ionic equation between ammonium sulfate and sodium hydroxide. So what is our reaction? And look like our reaction might look like something like this. I'm gonna write something, and if you see any mistakes, then we'll figure it out. SO4 to a negative, right? Plus, we're going to balance everything and writing everything after. Sodium plus OH give us sodium plus SO4 negative. Alright, so the physical states, all of these are, if it's an ionic equation, isn't it going to be all aqueous? In this case though, what is happening, we're going to have 2 of these. That means we have 2 of these, and we're gonna have oh, shouldn't it actually be 4? Hold on. Okay, do we balance? Let's see. What do I need to balance this? because for the ammonium sulfate itself, it would have been ammonium sulfate is 2 ammonia for the 1 sulfate. Okay, so I would have done this, right? And then this would have been 2 in order to cancel out that charge over there. And then this would have been 2 hydroxide because of what was happening here. And that is that. Does that seem fine now? And all is aqueous. All of it is aqueous. So all of it is gonna be aqueous. Any issues here? The SO4. Any issues? Any issues? Go ahead.
Sir, in this case, we wouldn't remove any of the spectator ions because then we wouldn't have any on the product side, right?
We remove any spectator ions?
Yeah, because like usually we remove spectator ions. But I'm just clarifying that in this case we wouldn't do that because then we wouldn't have any products.
We would.
Wait, let me look at the reaction because I'm doing this without looking at the reaction. Let me have a look at the reaction. Let's see. Oh. Okay. Hold on. Ammonia and water would be our. Wouldn't ammonia? Oh, so that's what I did. Alright, so if we look at it, right? Within an ionic equation, do we still keep the neutral molecules?
Sir, wouldn't you only use the ones that have the state like gas, liquids, and solids?
But ions will be aqueous. What do you mean specifically? Okay, so let's do the ionic equation. Let's do it step by step then. I need a space to do the ionic equation in though. I'm not sure if we're gonna have enough space down here to do all of the ionic equation. So let's erase this and write the entirety of the ionic equation, and then let's see if we are to condense versus if we are not to condense. Alright? So let's just do that. So with our entire thing, what we're doing is reacting ammonium sulfate, right, itself. So our ammonium sulfate would come looking like, wait, hold on, let me actually zoom in a bit. Alright, let me come over. Alright, so our ammonium, that's set to come over. Alright, so our ammonium sulfate, right? Which ions would that become? So our ammonium sulfate would evolve into 2 ammonium or 2 ammonia, 8 ammonium ions, right? And then we're gonna add now the sulfate, which is SO4 to negative, right? And then what we're gonna be doing now is adding 1 sodium ion plus a hydroxide ion. A OH ion. And then what are we gonna have? What are the products? On the product side now we're gonna have 2 now Na, 2 sodium, right? And then we're gonna react that now with SO4 2 minus, right? Then now we're gonna add 2H pluses
And then I go to school on the
Let's leave water. We're gonna leave water, right? We're gonna leave the neutral substances as they are, or are we going to ionize the neutral substances as well for the products? That's a question. Are we going to be leaving the water and ammonia that we get, or are we going to be leaving them off? Hello, guys. Go ahead. Yes.
You're going to include them.
Regularly, right? So H2O
Yeah, but you're not going to split them up. You want to split aqueous.
plus our sodium hydrox. Well, ammonia rather. Sorry about that. H3. All right. So we're looking at it like that. Okay. Now what's gonna happen here now? What's gonna happen here now? So all of these will be aqueous. What do we remove from the equation, guys? Go ahead.
The ions that appear the same on both sides.
All right, so we're going to remove the other things. Is that the idea of it? It won't use out the liquid. All right, so let's talk about what happens there then. Okay, give this thing a second. Right, so just do what it's doing. Alright, so we will cancel out, right, the ions, right, the spectator ions. The spectator ions would be the ones that just remain the same on both sides. That's what you said, right? And we're gonna keep the things that changes state. Is that what you're gonna? Is that what we're gonna do? Okay, tell me what to cancel out now. What do we cancel out?
Is the SO42.
Everybody agrees with that canceling?
Jay, remember
Yes,
that
sir.
it's two sodium hydroxide over the reactant side, so you need to put a 2 before the sodium and a 2 before the hydroxide.
Alright, and we cancel
And then
the
that would cancel out too.
canceling the sulfate, right? Canceling out the sulfate.
Yes, sir.
What else do we cancel out? Do we cancel out anything else?
Nothing, no, nothing else.
The sodium.
We cancel
Oh,
out
the sodium.
Sodium. So sodium turns from an iron to a metal well, this would technically be sorry, I didn't put the charge here. Alright, so let's see now. So what's the overall reaction here? So we can see that ammonia reacts with hydroxide to give us water and ammonia. Ammonium will react with that to give us. So that is the equation. Right. For
A 2 should also be in front of ammonia.
is it not
I
there?
don't want.
It's not there? Hold on. Oh, A 2 should be here. What? No, a 2 is there.
And a 2 in front of water too.
Oh, a 2 is for the ammonia. I added. Alright. So I didn't see that. Okay, hopefully they're being written. Alright, that is that. Okay? That should make sense. Alright, so here now, right, in module 2, to show the initial rate of the reaction between substance Q and substance R measured in the series of experiments with the following rate equation being deduced. So what does this mean? Somebody read this and tell me what it means. What does this mean? What does this mean? What can we tell from this equation?
The first substance Q is first order, and the second substance R is second order.
Lovely. And what is the overall order of the reaction?
3.
Third order.
Lovely. Right, using the experimental data from that. Okay, this is calculate the rate constant K. Interesting. Can we calculate the rate constant without the rest of the information in the table? I mean, sure we can, because the first thing we are asked to do is calculate the rate constant K. So what can we use to do that? We could use experiment 1, right?
Yes, sir.
Yes, sir. I transpose the front K and punch in experiment 1.
So K is equal to what? Rate divided by what now?
The concentrations of the reactant